I have went through, if you go into our class, you click on syllabus over here. I have adjusted the schedule and the homework has been adjusted accordingly. The dates of the first couple tests have been shifted. So that, alternate day, and I made 7.7 optional. Cause I had to give up a day somewhere, or we did no reviews somewhere. And I will make a video for 7.7 and let you guys watch it. But it won't be on, 7.7 won't be on the test when we get to chapter 7. As it is, the. The Mind Math Lab homework has been adjusted, I did it this morning. So that like all the due dates, you still have a whole kind of like 2 weeks thing. Let's go ahead and wrap up this section. I need to do. Yeah. Here I need to switch to. Share something different. Stop share. Share. Second camera. Alright. So we're almost done with 5.2, like the last part is kind of trivial here. And we had gotten, well, not really, some stuff that's important. I think maybe I'll need to push 5.2 as well, just to make sure we didn't actually finish it. Where we had, the last thing we had really talked about and used a little bit. Math 54. 5.2 continued. We had done ASTC. To show the signs of where stuff was positive. So sine and cosecant were positive here. Everything was positive here. Tangent and its reciprocal cotangent were positive here. And here was cosine and its reciprocal secant. And we went by all strippers take cash. Or all students take calculus if you like that one, but I don't think that's true. Or I know strippers take cash is true. If you got another acronym you like that uses ASTC, it makes sense and works for you, go for it. If it's good, share it with me. So we've seen, we have these functions, sine theta, all of our 6 trig functions. And this theta here is the argument. Theta is the argument of the function. That's what it's called, argument of the function. It's the angle. And theta can be anything. Theta can be a wide range of numbers. It can go from negative infinity. All the way up to 0. Up to positive infinity. So kind of like writing with that notation is a little bit idea from algebra. They have another notation that's you hopefully were introduced to it in algebra. 35, pre-calc 8. But I'll remind you of it here. It's called interval notation. And interval notation is when we have less than or greater than, we can use parentheses. If we have less than or equal to or greater than or equal to, we use brackets. And they kind of mix and match. But a bracket indicates what's going on. For theta here, we would say it's kind of handy to look at a number line and like have 0 in the middle, negative infinities over there. And like draw a pin or move a pin or a finger or something across the number line. Wherever your numbers start, that's where the interval notation starts. It starts at negative infinity. And then you do a comma. Start, comma, stop. With one of these bracket things going on. We'll talk about which one in a second. This is just like a general thing here. And we're going all the way up to positive infinity, so it stops at positive infinity. If it includes the number, we use the bracket. If it doesn't include the number or has less than or greater than, we use parentheses. Infinities are always parentheses. Because they are not a real number. This is hopefully a reminder. Now, if we look at sine theta and cosine theta. The values of these, this theta thing is the input, that's our it's called the domain. It's our input numbers. The output numbers, or what these values can reach or equal, it's called the range. And sine theta and cosine theta are both restricted to being between 1. So -1 is less than or equal to sine theta or cosine theta, which is less than or equal to 1. And in interval notation, we say negative infinity, or not negative infinity, -1 to +1. Since I use less than or equal to, I'm going to put a bracket here. And since I have my upper limit as that one, I'm going to put a bracket here. Like making a sandwich with the stuff and what's in the middle. And like the bread is like the outside of the sandwich are two numbers. And you can kind of look at like the bracket is if you keep the crust on. And like if you're one of those people that cuts the crust off, you got the parentheses. So the difference between that and this, as a reminder, -1 less than some value less than 1 would be -1, 1 with parentheses. Just showing you the range of options they could be. If we had it like that. So maybe I'll put a little squiggly line between it. This would be a bracket for the -1, but a parentheses for the +1. And if we had it the other way. We would have a parentheses for the -1 and a bracket for the positive. Those are like the 4 variations you can have for interval notation. So you can see how they match up. It's basically. Do we have an equal portion to our less than or greater than symbol? If so, we use a bracket, otherwise we use parentheses. Sine theta and cosine theta have an output like that. Oftentimes, and we'll get to the point where you'll see it a little, where we're using x instead of it. When we do like y equals sine x. And or y equals cosine x. This is where you see this range issue really pop up. We usually associate range with y and domain with x. But we can use theta instead. When we graph these, you'll see that the highest it goes is +1 and the lowest it goes is -1. And it makes a nice little like wave. I think we're doing that in, I don't know if it's in chapter 5 or it's definitely later or sooner. If we look at tangent theta and cotangent theta. This is y over x and this is x over y. And since x can be anything. And our y is like kind of, well, I guess if we're making a triangle, y can be anything. This has a wide range of numbers. If the bottom is really small and the top is really big, we get really like huge numbers. We have a value in the millions. It's not often, but yeah. The range here for these is negative infinity to infinity. Another way they say this very particular thing is they'll make a capital R and do another line through it. That's like fancy schmancy math notation for all real numbers. That way, if you see the symbol, you'll say, I remember that, I wonder what that was. And the R, it looks like R for real, stands for real. Secant theta and cosecant theta have a different range. This is R over X, and this is, nope, that's. Sorry, secant and cosecant. That's R over X, and this is R over Y. These can actually be any number but. -1 to 1. The way we show that is on like we looked at it on a number line. It can actually equal -1, so I'm gonna put a little solid point there, it can equal +1. It just can't equal anything in the middle. So it's kind of like this. On number line. And the way we show this in interval notation is we do the pin thing again. It starts at negative infinity. And it stops at 1. So I'll do -1. The negative infinity always gets a parentheses, the -1 has an equal portion, it's filled in, so we're gonna put a bracket. Then it keeps sliding, there's nothing going on for a little while, and it starts up again at 1. And it goes all the way to infinity. The 1 is included, but the infinity is not. And since it has like 2 different regions, we put this giant U in the middle of it. Tends to be like a fat capital U. This symbol means union. And it means the answer is in either of them. Like both are valid solutions, ranges. So if I look at some things, some values, and I said, like, cosine theta equals 0.821. We'll eventually see how to, like, today, we're gonna cover how to get that theta. But for now, like, is this possible? That's what we're gonna play a game, is this possible? Well, cosine theta was allowed to be between -1 and 1. And 0.821 is in that region. It's within the region. So this is, yes, possible. As opposed to something like cosine theta equals negative 1.7. Well, negative 1.7 is like outside the region. So this one's impossible. Can't happen. Effectively, what this tells you is that sine theta and cosine theta are either plus or minus 1.0, or they start with the 0 and have some decimal places. There's no other possible combination for sine and cosine. What about tan cotangent theta equal like negative 0.99? We go and we look at the region and the range of numbers that work with cotangent. All real numbers work. So yes. That's good, that's possible. Can I get cosecant theta equals 0? No, we can't, it's undefined. This is R over Y and R, if it helps, R is not 0. That's the obvious one, but it's 0, we wanted to look at this region right here. And 0 is in the no zone. A handy way to remember these have to be bigger or outside of 1. Is to remember the triangle looks something like this. And looking at the triangle, R is always the longest side. So sine theta being y over r, and cosine theta being x over r. We have a fraction with the bigger number on bottom. Like, this is a weird example, but like 19 over 20. That's less than 1. There's no way to get a number bigger than 1. And the only time it would actually equal 1 is when the top and the bottom are the same, and you're on one of the axes, you don't have a triangle. On my screen, at least on the Zoom camera. And then if you flip them over. This is cosecant theta is R over Y. This is secant theta, R over X. Big on top. So like 20 over 19, we have a number that's larger than 1. Or if it's negative, lower than negative 1. Ready for some more? Does anyone need this page up longer? Alright. So this part, this next stuff is like super duper important to calculus. So I'm gonna explain how I get it, that way you don't forget it. Oh. We had cosine theta was x over r. And I have sine theta is y over r, that's from our triangle. Now, if you don't like fractions like I don't like fractions, I like to say fuck fractions. Let's tell the fractions to fuck off. The way we do that is we can multiply both sides by r. I'll do this on each of them. Then I get r cosine theta equals x. And I get r sine theta equals y. Which is actually a good thing to remember, but not the end goal here. If we look at the triangle and we have like the x, the y, the r again. We had talked about the Pythagorean formula. Is x squared plus y squared equals r squared. Then take and plug that in right there, and I take and I plug that in right there. So I'll have r cosine theta squared plus r sine theta squared equals r squared. You guys with me on that one? Just a little plug and play substitution. When you have something square like that, if you're from your pre-calculus or algebra, the square applies to both of them. So I have r squared cosine squared theta plus r squared sine squared theta equals r squared. And we know r can't equal 0, because then we don't have a triangle. Which means r squared can't equal 0. Which means the next step is valid. I can divide both sides by r squared. If it can equal 0, you don't want to divide by anything that could potentially equal 0, that's bad. If I do that, I'll separate it out into just doing r squared over each of these. And my r squareds cancel and are replaced by ones on the fractions. And I get cosine squared theta plus sine squared theta equals 1. That formula, you're going to use the shit out of in calculus. I'm going to go with about a third of the time trigonometry comes up in calculus. This motherfucker is the solution. Like using this to like make things easier is the solution. This is very, very worth memorizing. Also, it's two alternatives. If I subtract sine theta or sine squared theta from both sides, this comes up a lot. Or if I subtracted cosine squared theta from both sides, that comes up a lot. These are alternate versions of the same equation. And oddly enough, and I don't know why, Most sources. Write the sign first. Sine squared theta plus cosine squared theta equals 1. They're the same. You can, when you have two numbers added together, you can just change the order and addition doesn't change. But if you're like going off of the, like the x squared plus y squared equals r squared. This is what kind of falls out. I don't know why they do sine first. They like sine first for some reason. But either of those is the same. So know those. If you need to, flashcard them. If you've never used flashcards. You'll learn enough shit, or if you, especially if you gotta take a bunch of like calculus 1 and calculus 2. You're gonna learn a lot of different formulas. I encourage flashcards, it'll help you memorize this shit and then you won't forget it later on. There's apps that do it nowadays, but I always did it on paper and like. There you go. I was always a cheap motherfucker though, index cards are hella big, I cut those bastards into like fourths. I'm sure I still have it at home, like on my desk, my dresser drawer, like a stack of flashcards this tall. That are all like fucking a fourth the size of an index card, cause I cut it in fourths. Cause I was a cheap bastard. Like index cards aren't that much, you get like a stack of 100 for like $1 or some shit like that. But did I wanna, nope, cut those fuckers in parts, that's cheap. Alright, let's get to the other two that come from this that are very important. I'm gonna do both of them. I'm gonna write down the original equation. And show how you get the other two. If I divide everything here by cosine squared theta. We're making the big assumption that cosine squared theta can equal 0, and we know it can't. But for the results of this, the numbers, you'll never have it where those were 0 in the first place. This is sine theta over cosine theta squared, written another way. And this is 1 over cosine theta squared. Just if it helps point it, show it to you. Well, that's tangent. So another version of this equation is tangent squared theta plus 1. Well, that's secant theta. Tangent squared theta plus 1 equals secant squared theta. That's important. The other one to get it? Instead of dividing by cosine squared, we divide by sine squared. That's a 1. That's cotangent theta and that's cosecant theta. So we're gonna get 1 plus cotangent squared theta equals cosecant squared theta. The order you'll probably use them, you will use sine squared theta plus cosine squared theta equals 1 the most. Then the next one that gets used is tangent squared theta plus 1 equals secant squared theta. This one comes up a reasonable amount of times. For some reason, this one doesn't just doesn't come up that often. For whatever reason, like this one doesn't come up that often, but it is there. This also includes like. If I subtracted 1 from both sides. I'd have secant squared theta minus 1. And if I subtracted 1 from both sides over here. I'd have cotangent squared theta equals cosecant squared theta minus 1. Those are just variants of the same one.
Are tests here gonna be written or online?
Regular.
So how strict are you with having the parentheses around the data? Or like,
As long as I can tell that it's meant to be the angle, I'm okay. For the long term. Yeah, I don't know who you're gonna have calculus. So you're better off getting in the habit of doing it. Cause you'll find later on that it is actually kind of helpful.
that helps.
Like, we'll see stuff like this. We'll have stuff like sine of 2x plus pi over 3. We'll see shit like that. But if you don't have the parentheses. Where does, like, what's part of sine and what isn't? So this is like a huh? So you're better off getting the habit of that. Like, if that's something like this came up and you didn't have the parentheses here, you get marked like. I said pi over here, like it look the same. Like this would definitely be wrong because I think you're adding pi over 3 to sine 2x. So, like, let's say we let's say we know sine of theta. Equals negative square root of 2 over 3. And we know cosine of theta is greater than 0. And we're gonna find cosine theta and tangent theta. There are a couple ways to do this. The way we did it before. Is he said, okay, what quadrant are we in? Cosine is positive here and here, so it's in one of those. Sine is positive up here. But our sign is negative, so we don't want that one. Sine is negative down here. We're having some thing down here. That's our theta. We'll have effectively, it's called the reference angle. We'll do more with that in a second, right here. That's the reference angle. And sine theta is opposite over hypotenuse. So if I draw that triangle a little bit bigger. I could say this is negative square root of 2. This is 3. We did this. Back a while ago. We did go. And we can find, this is x, and we can find this with x squared plus y squared, which is negative square root of 2 squared. Equals 3 squared, we can find x, and then go through and fill out what we need. That's one option. The other option is using this formula here. Sine squared theta plus cosine squared theta equals 1. I have sine theta is negative square root of 2 over 3. If I square that. Plus cosine squared theta equals 1. This is 2 over 9 plus cosine squared theta. And 1 is the same thing as 9 over 9, so that when I subtract 2/9 from both sides. I get cosine squared theta equals 7/9. we have something squared and we don't want it squared, we take the square root. Take the square root of both sides here. And I get cosine theta equals. There's a plus or a minus when you do square root. Square root of 7 over square root of 9. We know cosine is positive here. So we're gonna say cosine theta is the positive one. And the square root of 7 doesn't get any smaller, but square root of 9 is 3. You'll find if you solved this, you would have gotten x equals the square root of 7. This way very much works. I don't know that I enjoy it the most. I kind of like drawing the triangle myself. But if I were to ask this question on the test, and I didn't specify, you get to choose whichever way you like. Some people like using this method. If I wanted to find tangent theta. We know that's sine theta over cosine theta. And I've got negative square root of 2 over 3. Divided by square root of 7 over 3. Probably been a while since you've had fractions and fractions. As a reminder to clean this up, we flip over the bottom. And multiply the top and bottom by that flipped over part. We're effectively multiplying by 1. We have the same number on top and bottom, so we're multiplying by 1. Here the 3's cancel and the square roots of 7 cancel. Those 3's cancel. And I get tangent theta equals negative square root of 2 over square root of 7. And we don't like having radicals on the bottom. So we multiply top and bottom by square root of 7. And we get tangent theta equals negative square root of 14 over 7.
I said plus or minus, you can't have the minus, but it's cosine. It's only plus.
We can have a minus, but we had said we already know cosine is positive. So we had a pre-existing condition. So this force is positive. Ooh. The hell? Forces it to be positive. There's another way I could have gotten it. We said tangent squared theta equals secant squared theta minus 1. But secant squared theta is just 1 over cosecant or cosine squared theta. Cosine theta or cosine squared theta we had as 7 over 9. So secant squared theta is 9 over 7. And I put that in here. Got tangent squared theta equals 9 over 7 minus 1. And that's the same thing as 7 over 7. Do that subtraction, you get 2 7s. And we take the square root again. We don't like the square, we take the square root, it's a plus or minus. Tangent is negative in quadrant 4. So we go with the negative version. Tangent theta is negative square root of 2 or over square root of 7. And then we rationalized and got negative square root of 14 over 7. Oh, no screen yet. Was that not super fun? Was that not everything that you like? You wanna go home, put this on your fridge? Little magnet. Say, look what I did today, family. Thanks for the pity laugh. Let's take like a 10-minute break before we dive into the next section. I'm gonna be making you like grind nuts and bath for a little while. There's been a lot of heavy shit going on here. So let's give you a little break. In case I missed this a little bit ago. I thought I went over it the previous week, but let's take a look at that. Tangent theta is y over x. Let's start there. We already said y was r cos or r sine theta. And x is r cosine theta. We saw how that came about from doing sine theta and cosine theta. And we can cancel out the r's. And you get tangent theta is sine theta over cosine theta.
Thank you.
And since cotangent theta is 1 over tangent theta. It means we could just flip this and we're gonna get cosine theta over sine theta. Or cotangent. These are called the quotient identities. Now, I may not have said quotient identities. Does this look familiar from like previously? If I didn't, I thought I said it last week, maybe I didn't, I'm glad you asked. Those are well worth memorizing, those are part of your, in fact, they were listed at the same time as the whole Pythagorean formula list. And I didn't go over them because I thought I went over them already. That's fun. I hate talking about politics. I hate it, but like that fucking email right now just fucking triggered me. It irritates the shit out of me. Of course. As soon as you win the election, like within like a couple days. My cousin emailed me and says. You got any free money, buy XRP. And I did, and it's like I doubled my money already in like a month and a half. Cause they've been sitting on holding lawsuits with it being crypto friendly. That shit was gonna change. Alright. Something else that's kind of fun. Instead of using theta, I'm gonna use angle A and angle B. And this is X and this is Y and this is R. And if I look at sine of A. Sine of A, remember, is we're working with SOHCAHTOA here. Opposite over hypotenuse, Y over R. What trig function is Y over R for angle B? For angle B, Y is adjacent. So we've got adjacent over hypotenuse. And that's cosine. So these are called co-functions. Co-functions. We have sine of A equals cosine of B. Cosine of A equals sine of B. Tangent of A goes with cotangent of B. And cotangent of A goes with tangent of B. And secant goes with cosecant. Are we having fun yet? I'm not testing you on this. I don't know how useful this information is to like have memorized. Being able, you'll, if you need to do a certain angle on a triangle, you'll just go to that angle and look at opposite, adjacent, hypotenuse and go from there. You're doing this thing here, I don't know how useful it is. The following is useful though. But a fucking pain in the ass to remember. So we have, remember angles add up to 180 in a triangle. And a right angle is 90 degrees. So I have A plus B plus 90 degrees equals 180. Which means A plus B equals 90 degrees. And if I subtract A from both sides using some good old algebra techniques, I get B equals 90 degrees minus A. So I can replace that B right there with 90 degrees minus A. And I think the biggest pain in the ass, and something I still struggle with, is going which one subtracts which. I remember there's a 90 and I remember there's a fucking the angle. Is it like A minus 90 or 90 minus A? So like, there are points where this is useful, but like, I always have to stop and think about it. I'm not expecting you to memorize these either. If you do, you'll be doing a better job than I do. These are called the cofunction identities. Something that they do help with is memorizing some basic shit that we're going to do. So like, let's look at some examples here and we'll see how this plays out and what I'm even talking about in a second. Let's say we have sine of 30 degrees. This is cosine of what? Well, it's cosine of 90 degrees minus my angle here. So sine 30 equals cosine 60. If I did sine of 60, or I don't know, let's do cosine 30. There we go. Let's do cosine 30. This is going to be sine of 90 minus 30 So cosine 30 degrees equals sine of 60 degrees. If sine is 45 degrees, what do we get for cosine? 45. 90 minus 45 is 45. If sine has 90 degrees, what does cosine equal? Zero, right? 90 minus 90 is 0. And I'll do sine of 0 and oops. 0 degrees. If I do 90 minus 0, I get 90 degrees. So sine of 0 degrees is cosine of 90 degrees. The fact is, these zeros, 30s, 60s, 45s, 90s, these are called special angles. We're gonna make a little table with their values. Chance of things right. All right, let's take a look at a table of values here. Does anyone need this up longer? All right. So let's make a column that says theta. Make a column that says sine theta and make it kind of wide because you're gonna want room to write. Cosine theta kind of wide. And tangent theta kind of wide. And for theta, we're gonna do 0, 30, 45, 60, and 90. And you're gonna be doing fractions in this shit, so like, put some vertical spacing in there too to make it pretty for you. There is a very, very, very simple pattern to what these are. Like so unbelievably simple that you can be like, huh, I wonder how I could, that's like fucking magic. This value here, this is like, we're looking at sine of 0 here. This is the square root of 0/4. This one is the square root of 1/4. This is the square root of 2/4. This is the square root of 3/4. This is the square root of 4/4. Now these will simplify, but I wanted to like show you the pattern. 0 divided by 4 is 0, and if I take the square root of 0, I just get 0. Square root of 1 is 1, and square root of 4 is 2, so that's 1/2. Square root of 2 doesn't simplify, but the bottom is 2. Or square root of 2/4. In fact, the next one has a 2 on bottom here and a square root of 3. And finally, we have square root of 4/4, which is square root of 1, which is 1. Let me put some vertical lines in here, so, or horizontal lines in here so that we can like see what's going on. You guys see that pattern? So square root of 4 on bottom. And square root of 0 through square root of 4 on top. They just go in order. Cosine moves in the exact opposite order. Cosine starts at 4/4 and goes downward. So cosine of 0 degrees equals square root of 1 is 1. And basically, it's the column on the left just flipped over. I think this, we call these special angles due to the degree version. When we see these in radian version, we feel like, wow, that is kind of neat. It's got a nice little pattern to follow with radians as well. That's chapter 6 though, that's a couple weeks ago. Now, tangent theta, pain in the ass. If you want to memorize that pattern, we're still going with this. So I'm gonna do sine over cosine is 0/1, which is 0. First one is kind of easy. The first, the middle, and the last is easy. The middle one, or the 30 and the 60, are the pain in the ass. This is 1/2 divided by square root of 3/2. If I multiply top and bottom by 2, I get 1 over square root of 3. And if I rationalize this, this is square root of 3/3. This one is square root of 2/2 divided by square root of 2/2. I've got the same thing on top and bottom. Tangent of 45 is 1. This one, I have square root of 3/2 divided by 1/2 is, you simplify that, is square root of 3/1, which is just square root of 3. There's a reason why I'm showing this version here, as I'll show in a second. And finally, this is 1 divided by 0, which is undefined. Tangent of 90 degrees doesn't exist. That's no value. Those are worth memorizing. It may take you a while, this is definitely fucking flashcard. Yeah,
Just remember like. Something like.
these values right here are the most important. These other values, like this one right here, like these first two things right here, you do not need those columns at all. They are a pattern for remembering it and tell you, like a way to help you memorize it, until you've got it memorized. I would say make flashcards, like have one that says sine 0 degrees, and on the backside, what does it equal? Sine of 30 degrees, what does it equal on the backside? Mix all that shit up and keep going through those flashcards until you have it memorized. That would be what I would do. Until you do that, this is the handy little pattern that follows. Having this version memorized for tangent is helpful. Simply because if we do cotangent. It's 1 over tangent theta or flip tangent. So like cotangent of 30 degrees. If I stick with the 1 over root 3 and I flip it. That's the tangent of 30 right there. If I flip it, it's going to be root 3 over 1. Whereas if I flip this one, if instead I try to flip root 3 over 3, I get 3 over root 3, and then you gotta rationalize again. And you're eventually like, you will get that. But it's almost easier to memorize these two. And I'll be honest, I don't remember tangent 30 or tangent 60 ever. I used to have it memorized. But it doesn't come up often enough that I remember what it is. I remember sine, cosine, and then I will calculate tangent if I need it. Same thing you'll do here if you want cosecant theta. Just flip sine theta. And if you want secant theta, flip cosine theta. Like the book says, has like, let's walk through making a table of values for those. That's not fucking helpful. You're gonna be like, no, that's fucking too much. I ain't gonna remember all this shit. As long as you remember the relationships of cosecant being 1 over sine, secant being 1 over cosine, which we talked about before. And cotangent being 1 over tangent. I don't need to have them memorized for the upcoming test. But I will tell you part of the second test. I'm gonna give you it's called the unit circle. You're gonna fill in the, like, it'll be like no calculator, fill in degrees, fill in the radians, and say what each of these values are. So by the time we get to the second test, I kind of want you to have these memorized. Not on the first test though, like that's a lot to cover, and it's not helpful yet until we have the radians. Or less helpful until we have the radians. All right. Reference angles. We usually give it a hat, theta hat. And what it is, it equals the angle with the closest x-axis. So let's look at like angles in each quadrant. When we do angles going all the way around. That's our regular theta. Our reference angle in quadrant one, it happens to be the same thing. Over here, it's this angle. Which means like in quadrant two, the reference angle is really like 180 degrees minus theta. Here, if I'm on this line right here in quadrant three, the closest x-axis is going backwards. So here it's kind of like 180 degrees plus the reference angle equals theta. Or if I wanted to write it in terms of the reference angle, it's theta minus 180. And here, that's my theta hat there. This is the equivalent of taking the full circle and subtracting theta. Putting the last two ideas together is where the magic happens. This is the good shit. If I have 135 degrees. My reference angle here is 45 degrees, which is 180 minus 135. Now, where this magic comes in is we can relate it to theta in the first quadrant, doing that same reference angle of 45 degrees. And we can go, what is sine theta, cosine theta, tangent theta? These are all both √2/2. And tangent theta was 1. Sine of one, or this over 135 will have the same thing. Here we can do sine of the reference angle is the same thing as sine of 135. So over here, sine of 135, cosine of 135, tangent of 135 has all the same values as the reference angles in the first quadrant. And all you gotta do is pay attention to sine. Over in quadrant 2, x is negative, which makes cosine negative. And like we're doing all strippers take cash, only sine is positive in that region. So cosine and tangent are negative there. Let's say we're all the way in quadrant 3. We've rotated around 240 degrees. If I figure out my theta, my reference angle, this is 240, which is theta minus 180. 240 minus 180, I get a reference angle of 60 degrees. I can look at my sine of 60, cosine of 60, tangent of 60. And apply them over here to this. Give them the exact same values. Just pay attention to sine. Square root of 3 over 2, 1/2, and root 3. All strippers take cash, only tangent is positive there. So sine and cosine get the negative. That's kind of neat. Works in any of the quadrants, with any angle, I'm just using the special angles because I have those values memorized. But the same thing works with some fucked up angle. Let's say we're looking at 281 degrees. This is 270 degrees, so 281 is just past it. My reference angle is here, and it's 360 minus the 281, which is 79 degrees. So if I want sine of 281, cosine of 281, or tangent of 281, I can just do the sine of the 79 degrees, cosine of 79 degrees, or tangent of 79 degrees, and then pay attention to the sine. All strippers take cash, only cosine is positive here. Oop. So sine and tangent are negative. And this is where calculator comes in. This is less helpful on this version. I'll show both. I'm gonna do sine of, let me make sure I'm in degree mode. I am. I'm gonna say sine of 281. And notice it says. Negative 0.9816. That's the full answer there. And if I do sine of 79. I get the positive version of that. And I slap on the negative from being in the fourth quadrant. So if you want to have like a little pattern or recipe on what to do here. Like, we'll start off with step one. If theta is bigger than 360. Or theta is less than 0 degrees. Find the coterminal angle. Where theta is between that, 0 degrees and 360. Like add 360 or subtract 360 as necessary to get down into this region. Step two. Find the reference angle. Trust me when I say this, with practice. This becomes almost as easy as basic addition. You will get so used to it. Maybe not by the time you're done with trigonometry, by the time you're done with this class. But you'll be doing this again, using this stuff in calculus. At some point, you'll like be very, very comfortable with reference angles and immediately identifying what the angle is you want to use. And you won't even have to stop and think about this. Because it's just that useful. Step three. Find the trig functions you need with the reference angle. And then step four is use the right sign based on quadrant, or use the correct sign based on quadrant. Examples here real quick. So here, I don't like this value here, I'm gonna add 360. So I get sine of 240 degrees. That puts me in quadrant 3. Which means my reference angle is going back to the 180. Theta hat is 240 minus 180 is 60 degrees. So I'm looking at sine of 60 degrees. That is square root of 3/2. I applied this quadrant and it's negative here. So sine of negative 120 degrees is negative square root of 3/2. If I subtract for the cotangent, if I subtract 360, I'm down to 420. That's still not between 0 and 360, so I'll subtract another 360. And I'm down to cotangent of 60 degrees. This is 1/tangent of 60 degrees. And if you don't remember that, do the sine of 60 over cosine 60. You just memorize sine and cosine. You'll have root 3/2 over 1/2. So tangent of 60 is root 3. Which means cotangent of 60 is we flip that over. Make it 1/3. And we don't like the radical on bottom, so we multiply top and bottom. We're gonna get cotangent of 780 equals square root of 3/3. And we're in the first quadrant, so everything is positive here. So like 780 is like going around twice. And going 60 degrees. That's 780 degrees, going around twice and another 60 degrees. This helps going the other way too, if you know what the answer is, finding the angle. Finding the angle given a value. Well, like if I say find sine theta. Not sine theta, find theta. If sine theta. Is negative 1/2. So we'll look at the positive version of this. If sine theta is 1/2. We have theta equals 30 degrees. That's gonna be our reference angle. So I have 30 degrees here. I have 30 degrees here. These are my 4 possibilities. Those all have a reference angle of 30 degrees. Where is sine negative? 3 and 4. So sine of 30 is down. This would give us a -1/2 for sine down here, and this would give us a -1/2 for sine down here. So if I wanna find this angle, I gotta do 180 plus the 30. So I'm going around 180. Plus another 30. And I get 210 degrees is one of those thetas. And here, this is like going. This one over here, doing the full 360. And then subtracting off the 30. 330 degrees. So theta is gonna equal 210 or 330. Now let's take a look at some calculator work. For the theta hats that are not special. Make sure, pro tip. Make sure you're in degree mode. If you're working with degrees. And if the angle is a decimal. Decimal or has decimals in it, you're good to go. Just plug it in. Like if I have cosine of 211.35 degrees. Assuming you're using a scientific calculator. Cosine 211.35 degrees. I get -0.854. Straightforward calculator work for a decimal angle. Where it gets a little fucking shitty. Is, and you knew this was gonna happen, degrees, minutes, seconds. Let's say we had, I don't know. Tangent. 41 degrees. 21 minutes. This is the same thing as tangent of 41 degrees. Plus 21 over 60 degrees. We did the degrees to minutes conversions back in, the first section. That's where this comes in. Now you can either do this part first. Hit equals. And then say tangent answer if your calculator has an answer button. A lot of them do. Or if you've got parentheses. I can literally just use the parentheses and say tangent. Hit the parentheses sign to start it. And say 41 plus 21 divided by 60. And I hit end parentheses. And I have right now what I got here. And I just hit equal and I get my value. 0.88. Showing you with the answer version, I would do 41 plus 21 divided by 60. So I could write down like maybe a substep here, tangent of 41.35. And then I can say tangent of answer. And I'll get that same 0.88. If you want to do one of the weird ones, like cosecant, let's say we had cosecant of 187 degrees. Your calculator doesn't have a cosecant button. It does have a sine button. So treat this as 1 over sine of 187 degrees. 1 divided by sine of 187. Negative 8.2. And finally, and this relates to the question you asked me way back at the beginning. If you have something like they give you this, but they don't tell you what the angle is. Let's say we have like 0.09265. The button you're looking for is whatever this is, do the inverse button. This is the same as cosine or cosine inverse of 0.09265. Most scientific calculators have this, so you should have it on your scientific calculator. You may have to figure out how to use it. If I look on mine, right above cosine, I don't even know if we can see it very well. Oh, there it was, it's showing up. I have a little cosine and -1 up here. And it's in yellow, which is telling me to hit the button that has the yellow on it. Shift has yellow text right there. So if I want to do this, I'm going to do shift cosine. And notice that the cosine inverse popped up. And I'll put in 0.09265. When you're doing this is only going to give you the reference angle. You'll have to figure out what theta is based on quadrant, if you have that information. So here I have 84.7 degrees. Well, rounded. Approximately. If I did cosine of 84.7, I'm going to be off, but just a little bit. It's 5 o'clock. I gotta let you go. We will start 5.4 on Thursday. Godspeed.